So now we have a talk by Sérgio Xavier from University of Para, and he will talk to us about lecturing, so around exotic compact objects, traversable wormholes. So
Yes.
please.
Thanks for the introduction, and I also would like to thank the organizer for the opportunity to show my work here. And today I'm going to talk about this work that was made in collaboration with Professor Carlos Herdeiro and Professor Crispino. And I will start by providing a brief motivation to the work, and following that we're going to discuss the main findings of the paper, okay? So I think it's fair enough to say that most of the work presented during this meeting is somehow related with the so-called Kerr hypothesis, which states that the dark and compact objects in the universe are described by the Kerr metric of general relativity. And in order to challenge this idea, and there are several reasons to why to do that, I think you have at least two ways to do that. The first one is to say, okay, that compact object, it is a black hole. However, it is not described by the Kerr metric. And we saw some examples of other metrics that could describe this object, like regular black holes or hairy black holes, and etc. And the second path that you can follow is to say that object is not a black hole at all, so it doesn't have an event horizon. And so it is a horizonless compact alternative, also known as exotic compact object. And we also saw some examples of these objects during this meeting, like wormholes, Boson stars, and the list goes on. Well, in this presentation, we're going to follow the second approach by studying these compact objects called wormholes. And we're going to do that because there are previous results in the literature that tell us that some odds of wormholes could mimic very well phenomenology usually associated with black hole physics, like, for instance, the initial response to perturbation or the images of the accretion of matter around these objects. And from this model, this happens, at least for one of the reasons to do that, to why this happens, is because this model have light rings. So this raises the questions, do all wormholes have a light ring? And that was the question that we tried to answer in this paper. So to model the wormholes that we're going to study here, you choose this line element here that describes traversable, asymptotically flat wormholes. And by traversable here, I mean that an observer crossing the throat of the wormhole will not encounter any event horizon or singularity. And we also choose a coordinate system such that the radial coordinate here, labeled as L, covers the entire space-time from one asymptotic end at L equal minus infinity to another asymptotic end at L equal plus infinity. And in order to study these light rings in these geometries, we follow an approach using this paper here by Pedro and Professor Herdeiro, where they assign a topological charge. They assign a charge to each light ring of the space-time. And by doing that, they were able to prove this theorem that states that any black hole under certain conditions will always have at least one standard light ring. And the meaning of standard will be clear in the next slide. Or in other words, you can say that you can state this theorem like the total topological charge of a black hole is equal to -1. So there should be a 8 here, I'm sorry. And so in practice, what this means is that if you take a static black hole, for instance, they always will be in this kind of configurations here. So they always have at least one standard light ring represented by this red circle here. Or if it has more than one light ring, the additional light ring must come in pairs, with one of them be an exotic light ring represented here by this yellow color. And in fact, the idea of assigning a charge to a light ring was introduced in this paper here, where they study some trivial horizonless compact, topologically trivial horizonless compact objects, and they found that the topological charge of this object would be equal to 0, which means that this kind of object, like boson star, always have light rings coming in pairs, with one of them the exotic one. Okay, but how do you assign a charge to a light ring? you do that by starting analyzing this function here, which is the effective geodesic potential. And this function h is interesting because its critical point represents the position of the light ring in the space-time. And from that, you have then a way to classify the different kinds of light rings that you have. So for instance, if the light ring is associated to a saddle point of this effective potential, this means that this light ring will be called a standard light ring because it's the kind of light ring that happens in Schwarzschild or curved black hole, and its charge will be equal to -1. In the other case, if the light ring is associated with an extremum of the effective potential, this light ring will be called exotic light ring, and its charge is equal to +1. But how do you compute this charge? To compute this charge, you first need to construct a vector field from this potential, and this vector field is essentially the normalized gradient of the effective geodesic potential. And then, so here in the left, you are seeing the behavior of this vector field for a specific model of wormhole. So here, in the horizontal axis, you have the radial coordinate, whereas in the vertical axis, you have the angular coordinate. And this disk here represents the light rings in this space-time. So the throat of the wormhole in this diagram here is located at L equals 0. So this red color here represents a standard light ring, whereas this yellow color is associated to exotic light ring. So the idea to assign a charge to each one of these light rings is associated with how this vector field changes its behavior close to each one of these light rings. So for instance, you can see for here how the vector field changes its behavior close to our standard light ring and close to our exotic light ring. And notice how the vector changes its radial direction, for instance. And from that, then, you can assign a charge to each one of these light rings by computing this integral here, where this capital omega can be obtained by this polar decomposition. So the idea then is to construct a counter around one of these light rings, like for instance this one here, this red one, which is a standard light ring. And then you perform this integral in a given sense of direction. Like for instance, if you perform this integral in a counterclockwise way, you can see that the vector field here, as you move in a counterclockwise way, the vector field winds in a clockwise way. So in a sense positive to the sense of the circulation of the integration. So for this particular light ring here, its topological charge is equal to -1 because the wind of the vector field is opposite to the circulation. But you can see that for this another light ring here, the exotic light ring, the circulation and the winding of the vector field are in the same sense. And because of that, after you perform this integral, this light ring will have a charge equal +1. But this approach of assigning a topological charge to each one of the light rings is the additive one, which means that if I had chosen a counter that such that inside of this counter you have both the light rings, the topological charge of this region here will be basically the sum of the charge of each individual light ring. So for this case, it would be -1 + 1, it will be equal to 0. So this gives you an idea on how to obtain a topological chart for entire space-time. What you need to do is basically then choose a counter such that after you take appropriate limit, this counter covers the entire space-time. And this was what we did in this paper. So we choose this counter here such that it covers the throat of the wormhole, and then we perform that integration after taking the appropriate asymptotic limit in a way that this counter will cover the entire space-time. And these appropriate limits are the asymptotic limit by making this R here go to +infinity, and therefore you are covering both sides of the throat of the wormhole, and also the X limit by making this delta here goes to 0. And after you do that, what you found is that the topological charge for these wormholes are equal -1. So it is the same value for the case of black hole. So what this means? This means firstly that all traversable, asymptotically flat wormhole that is connecting two different universes, it always has a light ring. So it is always a ultra-compact object. And besides that, and this result is independent if the wormhole is symmetrical with respect to the throat or asymmetrical with respect to the throat. And besides that, we also prove in the paper that if, in fact, if the wormhole is symmetric with respect to the throat, it always hosts a light ring precisely at the throat. So to conclude, what we found in these papers in this work was that from a point of view regarding light rings, wormholes and black holes are in the same category. Also, of course, we can discuss about the dynamical viability of wormhole as black hole mimickers, since they do not have a mechanism formation known. But still, regarding light rings, they are in the same category of a black hole, and therefore they are always a ultra compact object. So that's it. Thank you for the attention.
Thank you very much. Do we have questions? Yes, please.
Thank you for your presentation. The beginning of your talk, you stated that wormholes and all these compact objects can mimic some aspects of black holes. And you talk about one, that's light rings, right? Is there a limitation in these compact objects, like this specific thing, they cannot mimic, they cannot be like a black hole?
Well, okay. Well, when I say that they can mimic black hole, I'm not sure if they can mimic absolutely in all range of the phenomena. For instance, when I show one of the plots was showing that the initial response of black hole of wormhole superturbation could be very similar to black hole, but in later stages you could see some signatures of the wormhole that are not present in the black hole case. So I'm not sure if there is, or at least I cannot remember now if there is something that it is exclusively to black holes that cannot be imitated by other exotic compact objects.
For example, a collapsing star can form a wormhole, like.
Well, that's a tricky question because, at the best of my knowledge, there is no dynamical mechanism formation to wormholes. So, for instance, there is no model like that of a collapsing star collapsing, and instead of forming an event horizon, it will form a throat, etc. So, I cannot answer that question.
Okay, thank you. It's an open question.
Yes.
Thank you.
Thanks for the question.
More questions? Maybe I have a naive one, but can there be some configurations which would have topological charges more than one in absolute value?
In absolute value, well, so the contribution to the total topological charge always comes with a difference precisely of one unity. So would be +1 or -1. I'm not sure if there is some kind of configuration that could be I'm talking about single object, because if you take, like for instance, several black holes, I think you could have topological charge more than like +2 or +3, right? I'm not sure. Yeah.
Well, if you are thinking about black holes with scalar hair, I think that's the total topological charge is still -1.
Yeah. But I mean, if you have more than multiple black holes, yes. Yeah, I'm not sure if you could have a single object with topological charge different than +1, -1, or 0. At least I don't know.
So if you change the boundary, in principle, you can have almost anything.
Yeah, yeah, because the computation of the I think I made some. Okay, because the computation of this topological charge is strongly dependent of the boundary condition that you put in your model. So maybe you could construct a boundary condition such that you have a different topological charge other than different than unity, right? But I'm not sure. I don't know at least.
Yeah, that was more of a curiosity.
Yeah.
There could be, I mean, say you take some vector field. I guess you could construct a vector field which would have a bigger charge. But
Yeah.
I don't know if some objects could lead to that. Or,
Yeah.
but it was just
Okay.
out of curiosity.
Okay.
Thank you.
Thank you.
More questions? Yes, please.
So in order to arrive in this result, you only assume, about the wormhole, you only assume that it has this symmetry around the throat, and you don't do any.
Oh, we didn't have to assume that there is any symmetry between around the throat. So this result is valid to both symmetric and asymmetric wormhole with respect to the throat.
Okay.
So yeah.
I think I saw that in the final remarks.
Sure. Because there, this is a small result. I'm not saying very small, but it is another result that we prove that if the wormhole is symmetric, by the properties that the effective potential will have, you can prove that it will always have a light ring at the throat. But this is valid only for symmetric wormholes. So
Okay.
if they are asymmetric, you cannot
Okay,
get.
so this is like for the position of the wormhole.
Yeah, exactly.
The
The result about the topological charge, it almost tells you that space-time has light ring. It does not tells you how to find them or where precisely the light ring is. So here is another result that we can, besides that the wormhole will have light rings, if it is symmetric, you can locate one of these light rings at the throat. So.
Okay, but I see that for the first result, you have this is for the traversable universe.
Okay.
Thanks.
More questions? So if not, let's thank Sergio again.